Okay guys, so last video we talked about preparation of haloalkanes from alcohols, right? So this one we're going to talk about preparation of haloalkanes from alcohols again, but with a different method. So I'm going to show you this reaction now. So this is the next reaction you got to learn, okay? So ROH plus PCl5 giving RCl plus POCl3 plus H. Okay, so this is the next reaction you got to learn. Now, your book has no specifics on this, so you can, instead of to have a bromine, you can have ROH plus PBr3. PI3 is generally, PI5 is generally unstable, so you don't use this to prepare iodides generally. Okay, you can see why PI5 is unstable, right? Because of crowding, the acid bonds become too long, that type of thing. Okay, so that's basically it. Now, I thought I'd discuss the mechanism of this reaction. So, once again, if you guys are not interested, you guys can please fast forward, okay? So, there is one important trick for this mechanism, okay? The trick you got to remember, which you'll be using in every other mechanism, probably in your life, is that if you want, you are always allowed to remove H plus as and when you please. Okay, so this is the trick you gotta remember. You can remove H plus as in if I have, suppose, say some compound like this. Okay, so say R N H3 plus, right? And this is irritating me. What I can do is I can write this minus H plus. So I remove a H and I remove a plus to get RNH2. Okay, but this is called deprotonation. Now we just do this without thinking much, okay? Because when you guys are going to start writing mechanisms, you guys are just going to start doing this, just writing minus H plus. Since this is the first time you guys are probably hearing this, I will explain to you why we write minus H plus and why it's okay. Afterwards, we're going to take it to be implicitly defined and move on. Okay, so let's do that quickly. So you are going to consider water, which is always in the medium generally, to have lone pairs. And the good thing about water having lone pairs is that it can act as a Lewis base. And because it can act as a Lewis base, what Lewis bases do? They can abstract a proton. And another word for proton is H plus, right? So we assume that, for example, in this RNH2, NH3 plus, we'll draw it in the proper form, right? So we'll draw it like this. RNH2 and H. This is how it was, right? We're going to assume that the water will here, with its lone pairs, is going to call this hydrogen and say, you come up with me because this nitrogen isn't treating you that well, right? So what he's going to do is he's going to say, anyways, the nitrogen is going to be pulling the electrons from both R and H, right? So this hydrogen is going to be electron deficient also, like as in the electron is going to be pulled that way. And since this nitrogen is a positive charge, the electron is going to be pulled that way very high, very strongly, right? So oxygen says, I'll give you my electrons. So he dumps his electrons in this guy. Hydrogen cannot have two bonds, right? So he said, let's go off this bond. So since he let's go of this bond, both these electrons fall onto nitrogen and the positive charge goes away. So you're left with RNH2 and you're left with H3O plus, right? We just don't write it. So we say, since according to us only this substrate matters, so we say it was H plus was removed, right? So we write RNH3 plus minus H plus. Where did H plus go? It went with water, okay? Gives me RNH2. Or if you have, say, a halide ion, right? For example, if you have, say, chloride ion, he can do the same job, right? He can remove H plus S and become HCl. Water can remove it and become H3O plus. OH minus can remove it and become hydroxide ion. So we assume that there will be some base in the solution who's going to remove this. Then you can ask me, well, Hari, what if there is, it's only an acidic medium, right? The pH will not change between a reaction. So that's why we say, okay, then you have water, right? You still have water, and water can always abstract the proton, right? So that is the argument behind this. See, as I've said, mechanism is a way for you to convince yourself logically as to why a product comes, okay? So whatever logical step you can argue with somebody, those steps are always allowed in a mechanism. So that's the deal, okay? So this is a step which you'll see in many reactions, many mechanisms, is minus H plus. So I'm just letting you know, okay? Since we're talking about this, I thought I'll confirm one more doubt which I had for a long time, which is, see, I have a bond, right? Like this, and I say these two electrons are plonked onto OH, onto the oxygen. If this bond breaks, for example, and you get R plus plus OH2. That is, these two electrons compensate one positive charge, right? But then we also say Cl chlorine atom, you add an electron to it, it becomes Cl minus. So this looks like, one charge is like one electron, right? So one charge seems to be one electron here. And here two electrons is satisfying one charge. So I was super confused with this when I started, okay? And just in case you guys are confused with it, I thought I'd let you know. The answer is actually pretty simple. The answer is just that if you got a loose dot structure, you can actually find out. This is how the bond looks, right? H. So H also you can draw the dot structure. Another H. Right? Oxygen is supposed to have 6 electrons, if I'm not wrong, right? Okay, so these two will be coordinated, right? This is a coordinate bond, remember? These two will be here, and I have 2 more electrons here, right? And we say this is a plus charge because oxygen lost its lone pair. Now, when I say this bond breaks and gets plonked on top of this guy, right? What basically happens is, see, this electron is already oxygen's. So, when this bond is breaking, the net effect is that this electron of the R group, right, is getting added to oxygen's family, basically. So, it's like another electron like this. So, anyways, the positive charge gets cancelled by only one electron, and who oxygen has 8 electrons, right? 1, 2, 3, 4, 5, 6, 7, 8, yeah. So, that's basically the trick, and this guy lost one electron, you get an electron. So, charge is always conserved. One electron is always one charge, okay? It just looks confusing because we draw the bond shifting like this. Remember that we're always mostly talking about coordinate bonds. We're mostly talking about covalent bonds in organic chem. So, one electron already belongs to this guy. So, the net gain this guy is getting is only one electron, okay? So, just so you guys had that doubt, if you guys had that doubt, you clarify it, right? So, now let's do this reaction. This reaction is pretty simple. We're going to write ROH, okay? So we're going to draw lone pair, and the first step in any mechanism is what? Is to identify the players, right? So the player is this guy and PCl5. Now you guys know the structure of PCl5, right? Chlorine, 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 and you have axial bonds. And axial bonds are longer than equilateral bonds. Remember, because of more repulsion and stuff, sp3d2, sp3. This will be sp3d, sp3 dehydration, right? Not d2. So that's one of the arguments. Okay, so now basically, you gotta see once you write the players down, you gotta try to think of how they interact with each other, right? And you cannot see any obvious interaction except for the fact that, see, this phosphorus, this poor guy, right? He's getting mugged up electrons like nobody's business. Chlorine is pulling, this chlorine is pulling, this chlorine is pulling. Everybody is pulling. These are not coordinate bonds. I'm just showing the direction of dipole moment. Okay. So everybody is pulling electrons in this guy. Poor thing does not have a single electron. Okay, he cannot say anything is mine because everybody is pulling, and they don't cancel out also, right? They're not a pentagon. They are not in the same plane also. So dipoles don't cancel out either. So he is losing electrons like crazy. And you know our oxygen, right? He is a very benevolent guy. He loves to donate electrons, right? So he's gonna donate this guy and put him out of his misery and stuff. So if you guys remember, in the first lecture we talked about, you take this, you draw the coordinate bond, and then what will happen and all that stuff. So you get a coordinate bond, this will get a plus charge, this will get a minus charge, right? But then phosphorus will have 6 bonds. Phosphorus cannot have 6 bonds. So what is he going to do? He's going to part off with this bond, okay? When he parts with this bond, what happens? He loses an electron, so the negative charge goes away, and he gets 5 bonds again. So you guys have watched the first video, so this should have been clear to you. If not, I suggest you do watch the first video again because this is a fairly important step. But if you are to write it in shorthand, I'll just write it like this, right? So this attacks and you get this. So what do you get? Your OH, you got a positive charge. I just lost my lone pair. And you got P. I'm going to write this as PCl3 with a chlorine, okay? And Cl minus. So this is what's there in solution so far. Now what's going to happen is, let me erase this top part now. Right? Now what's going to happen is that, the same story, right? Remember we got R, OH2 plus whatever, oxygen with the positive charge is attached to R and we got an X minus in solution, right? Similar to that, you got R attached to the oxygen with the positive charge and an X minus in solution. So you can expect the same type of argument to a certain extent. So the argument I'm going to propose is, this guy is going to attack my R, right? Because of the same argument. This guy is taking on electrons, so he has no electrons, he has delta positive, delta negative, they want to attack, right? And this bond is going to get long down to here, okay? So far so good, right? Because R, again, same argument, R cannot have pentavalency, blah blah blah. So you get RCl plus, you are left with what? OH PCl3 with a chlorine, right? So till now, what is it that you've got in solution? You've got an RCl successfully, and you have this weird looking compound. Now, anybody who can tell me the name, who can tell me that they've seen this compound before, right? I think you guys will receive a Nobel Prize because this compound doesn't exist, and it doesn't exist for obvious reasons. It's highly unstable. Okay, so the molecule is going to try to escape this type of a configuration, right? And what it does to do that is, it says, okay, remember this step when I took the R, O plus, H, PCl3 chlorine, and I chlorine attacked this guy, and I shifted this bond on top of him. That created a very unstable product. So what we're going to do instead is we're going to say, okay, so that's very unstable, we don't want that, right? And obviously that's not formed also. See, you see the reaction first and then you try to rationale why the products came. So this is not going to be a product, so this guy is obviously not landing on top of the positive charge. You can also convince yourself saying, oh, it's because he's unstable, okay? So we're going to have to think of another way to argue this out. So maybe this bond does not get plugged onto oxygen. Maybe instead of getting plugged onto here, it just shifts, like it just pivots across the oxygen and gets plugged onto here. Completely possible. He could have also plugged onto hydrogen, but oxygen and hydrogen cannot have a double bond. This is possible. Oxygen and phosphorus can have a double bond. Okay? So if that happened, right? We just look at the possibilities here. Because that's pretty much the only way to escape this right now. So if instead of this happened, you'll still get RCl, but now you'll get OH. The plus charge didn't get neutralized now, right? So plus, you got PCl3. There was a double bond which formed. So once again the same argument, right? If you have a double bond here, 1, 2, 3, 4, 5, 6. You'll have 6 valency. Can happen. So this chlorine will leave, right? Phosphorus needs to maintain its valency. So we put double bond here and the Cl minus. So this bond is shift here and this bond leaves, right? The oxygens get plugged onto chlorine. So plus Cl minus, right? And then what happens? The final step is that the oxygen still has a positive charge. So I know what I can do. Remember I told you what? I can write minus H plus whenever I want to, right? I could have written it here also. In fact, I could have written minus H plus here also. I would have done the same exact thing, right? You remove the proton, you get O without a charge, and then this shifts, so you get this leaves, so you get still the same product. But it's generally advisable to write it in the end when you know where everything else is, right? Because for example, now we know that there's a chloride ion. So that chloride and this H plus will join together and form HCl as another product. So we know that also now, that's good. When I remove H plus from this, it's like removing this, plonking these electrons on top of this guy, so the positive charge goes away. Right? So what am I left with? If I just remove these guys, I'm left with this compound, POCl3, which is a good compound. You've got a POCl3, right? So POCl3. So this is how you write the mechanism for the reactions. And this is how you will not forget the either molar, stoichiometric coefficients. You won't forget that, because if you write a mechanism, that's exactly how it happens. So the stoichiometric coefficients will work out, and you won't need to memorize the reaction. Okay, so that's something you want to keep in mind. It's pretty fun to actually write down these mechanisms. So give it a shot, right? And we'll discuss if you guys have any other doubts later, right? So this is basically the reaction ROH plus PCl5 giving me these three products, right? And RCl is the one we want. So that was this lecture. We will see some more methods of preparation in the next one. Okay, see you guys then.